Good morning. I am Haijun Su, professor in the Intelligent Design and Robotics Laboratory in the Department of Mechanical and Aerospace Engineering at The Ohio State University. This talk is a practical guide to using large language models on kinematics problems. The aim is not to delegate mathematical judgment blindly. It is to build a local human AI workflow that turns source material into runnable code, numerical examples, and validation evidence. We begin with a paper recently published in Mechanism and Machine Theory on 6R inverse kinematics. Human experts chose the decomposition, supplied the task requirements, and designed validation. The coding agent implemented the pipeline, called algebraic tools, and iterated on tests. This talk asks whether that loop transfers to a broader set of classical kinematics problems. The expansion covers three families. Planar and spherical linkages have relatively low degree algebra and known branch counts. Spatial SS dyad synthesis introduces a delicate matrix polynomial. Stewart Gough forward kinematics requires exact symbolic elimination. The common thread is validation, but the evidence must adapt to each family. Before posing a hard question, make the local environment executable. Start with the source PDF or chapter, a local Python environment, a computer algebra system such as Mathematica, and a sandboxed agent that can write, run, inspect, and revise files. The goal is validation-centered tool use, not autonomy theater. Every executable prompt needs 4 blocks: context, task, requirements, and deliverables. Ask the agent to produce a script, an example, a command log, and a report. More importantly, state the checks up front: residuals, root counts, planted roots, branch coverage, and exact arithmetic when needed. With that setup in place, we move through 3 case studies. Notice that the mathematics gets more delicate and the role of expert guidance changes with it. The first family is planar and spherical linkage problems, 4-bar analysis, planar RR and PR dyad synthesis, and spherical RR dyad synthesis. These are good first tests because the literature gives an explicit formulation, expected branches, and direct residual checks. The agent should read the source, implement it, enumerate the branches, and verify the example. For these linkage cases, one structured prompt was often enough. The important result is not that they are easy. It is that a well-scoped source, an expected solution count, and a direct residual give the agent an unambiguous acceptance target. The SS dyad case is different. It is a 7-position spatial synthesis problem whose formulation becomes a matrix polynomial. It is an excellent stress test. The mathematical object is documented, but expanding a determinant can create enormous intermediate expressions and severe numerical sensitivity. The first solver failed in a useful way. It misread details in the source, formed unstable determinant expansions, and lost discriminating coefficients through cancellation. This is exactly why an agent must produce inspectable intermediate data rather than only a final answer. The expert correction was to solve the matrix polynomial directly through a companion pencil. We keep finite real eigenvalues, use singular value decompositions to recover geometric parameters, and then verify the recovered chain length. The key human contribution was choosing the stable formulation, not typing code. With that correction, the solver recovers all 20 real solutions and the planted root, with very small residuals over the 7 frames. The comparison makes the lesson concrete. A mathematically equivalent looking root can be computationally unreliable, so validation must drive revision. The third family is Stewart Gough forward kinematics. Given 6-leg lengths for a general platform, recover all assembly configurations. The study parameter reduction turns the geometry into a symbolic elimination problem with a characteristic polynomial of degree 40 and as many as 40 configurations. Here, prompt specificity matters even more. The successful solver follows the published sequence of determinants, null space parameterization, substitutions, resultants, and GCD extraction. Exact integer or rational arithmetic is non-negotiable. Changing the elimination order or using floating point symbolic algebra can change the recovered degree. The reported evaluation recovers the known root and the degree 40 polynomial in Mathematica. Compared with the SS case, less iteration was needed because the prompt preserved the published sequence. That is a success in faithful translation, not evidence that the agent independently invented the elimination method. Across the three cases, the trust boundary shifts. Explicit low-degree problems can often be implemented from one structured prompt. Delicate numerical systems require expert diagnosis of a stable formulation. Order-sensitive symbolic problems require the algorithmic sequence and arithmetic mode to be encoded explicitly. The practical result is a workflow, not a single answer. Source material and the local toolchain feed an agent, and the outputs must be scripts, numerical examples, and validation reports. Set up a dedicated local task folder before solving. Include the source, refined prompt, code, examples, logs, and reports. Verify that Python and the CAS are callable from the same environment. This turns a conversation into a reproducible computational experiment and makes failures recoverable. The operating loop is straightforward: generate, run, inspect, and validate. Require a runnable Python or Wolfram script, preserve intermediate coefficients or roots where useful, and write a concise report. Then check traceability to the source equations, solution counts, residuals, tolerances, and singular case behavior. No validation target means no trustworthy conclusion. One final timing caveat: this work was produced in late 2025 and early 2026. Coding agents now come with powerful harnesses, reusable skills, and richer multi-step execution loops. These tools can improve implementation reliability, but they do not by themselves prove that the system can choose a new symbolic strategy without expert guidance. The takeaways are fourfold. Start from a proven workflow, give the agent real tool access, keep the human as the method selector, and treat validation as the deliverable. If you do that, an LLM can be a useful collaborator for kinematics engineering without expanding the trust boundary beyond the evidence. Thank you, and I welcome questions.